So I am excited to present our first speaker, Benjamin ŠTULAR. Benjamin is Principal Research Associate at ZRC-SAZU, and he's an Associate Professor here at ZRC-SAZU. He has been deeply involved in geospatial analysis and data science application in the humanities for over a decade. Recently, he has focused on AI application in these fields, contributing significantly in the development of several AI tools and related educational content. So, Benjamin, mic is yours.
Thank you. And a warm welcome to everyone here and everyone online from me as well. I will present the work that we have done together with Edisa so that she can focus on moderating this event. The presentation, Data Conversations Made Easy, is about how generative AI can help us do more with our data and do it more efficiently. The presentation aims to bring this topic closer to non-AI specialists, and it is primarily aimed at people working with data in the cultural heritage sector. While the examples we will show are mainly from archaeology, the principles apply to anyone working with data in any forum. Whether you work with databases or your job involves responding to a ton of emails each day, you work with data. I, for one, am excited about the future where the tedious task of sifting through data is taken over by AI and I can concentrate on my actual work. This process is already underway and AI is already changing how we interact with our data. It's safe to say that 2023 was the year of large language models, or LLMs as we affectionately call them. Where were you when you chatted with ChatGPT for the first time? In 2023, the LLM arms race took off, but it soon turned into the race for efficiency, and we are now at a stage where we can run open source models on our desktops. But right from the start, companies and individuals alike have been looking for ways to leverage the power of LLMs with their own data. Generative AI is changing the way we interact with our data, and there are many ways to do that. And I think it's fair to say that 2024 is the year of AI connected to data. So let's take a look at the different ways LLMs can work with our data. If we have a few million euros to spare, we can train our own model. Realistically, we have a choice between fine-tuning model and connecting a model to our data. The choice will vary from case to case. However, fine-tuning a model still requires a dedicated team of experts. Thus, connecting the data is currently the optimal solution for most of us. It requires the least effort and almost no expertise. The quality lags behind, but it is still far better than anything we have seen before, and also it can be up to date. There are many different ways to connect LLMs to data. I will only mention 4 that are currently the most common. First, you can use a special type of AI chatbots called code interpreters to translate natural language questions into code that analyzes your data. The second, and by far the most popular, is Retrieval Augmented Generation, RAG. This method essentially allows you to chat with your data. Third, complex solutions can be set up for production use cases. And fourth, AI agents can do the work for us. Today, I will talk about the first 2 options, code interpreters and RAG, and our keynote speaker, Ronald Harasim, will present a complex full-stack solution. AI agents will be the topic of our next event. The method we choose depends on what is probably the most important boring thing in the world, data. In cultural heritage, we usually encounter 3 types of data. The first type is structured data, that is, your existing databases. The second type is semi-structured data, such as a printed catalog of monuments. And the third type is unstructured data, such as your folder of PDFs or your institution's website with all the manuals and rule books. We all love those, don't we? So let us take a look at how AI is changing the way we interact with structured, semi-structured, and unstructured data. First, we will look at structured data. We will show how AI is able to analyze our data, how it connects different types of data, such as spatial data, text, measurements, and even photos. All the data we already have, but which is too big for a single human to memorize and make sense of in our heads. The way the computer stores content is not aligned with how we as humans remember and connect to information. We remember information in relation to people, time, and places. We are inherently visual, and we create associations and connections that are unique to each of our life experiences. Computers, on the other hand, like to organize data into database structures, whereas our mind tends to think of relationships. To efficiently store data in a computer, we must first break it down into its smallest components and then reassemble them into a coherent structure. This process is known as building a structured database. However, because this is so different from our way of thinking, we need training to work with databases and even more training to analyze and build them. Until now, that is. Let's have a look at how AI is dramatically changing the way we can analyze such data. For data analysis, we need a specialized AI called code interpreter, for example, OpenAI's code interpreter or Open Interpreter. As an example, we will look at ARCAS, a database of Slovenian archaeological sites that holds about 500,000 of data points. This is not super large, but far more than any human can remember and process without the help of a computer. Existing web applications for ARCAS enable us to query the data, but no advanced analysis is available. That is why we leverage the AI code interpreter and built ARCAS AI Data Analyst. It's an AI chatbot that can analyze the data on Slovenian archaeological sites. Let's have a look. In the familiar interface, we can type in any language. Score 1 for AI because, as you may have noticed, the web application and data are in Slovenian only. Let's choose one of the prompts offered and click, for example, on his square test. Data analyst imports the required Python packages and creates the corresponding code for each of the 6 steps. At each step, it will run the code on the ARCAS data and provide the results for the next step. The first result is an interactive chart that we can adjust to our liking. There is also a tabular result and the final summary. We have asked ARCAS AI about the correlation between chronological period of sites and site interpretation. We got top 5 positive and top 5 negative correlations. For example, the strongest correlation is among the Roman period and early Iron Age sites with cemeteries. This is completely new insight in information and would not be possible without an in-depth analysis. It is also objective and repeatable, so it is scientifically sound. However, the prompt seems rather daunting, doesn't it? It involves 8 steps: loading data, filter data, create contingency table, and so on. This is necessary because current LLMs cannot plan well. Therefore, for a multi-step action like this, human prompt engineering is needed to guide the LLM step by step. But this prompt specifically is only so complex to get the user to the final result with a single prompt. When you will be using this in your own analysis, you can proceed step by step and ARCAS AI will guide you. Here, for example, ARCAS AI suggests different statistical methods that are best suited to this particular dataset. So this was unstructured data. With the help of AI, we were able to effortlessly search for hidden meaning in our database. Our complex analysis provided new insights into the data that were previously only accessible to data analysts. This gives us the unprecedented opportunity to explore, experiment, and simply play with the data, even if we are not data specialists. Now, let's move on to semi-structured data. An example of semi-structured data is this furniture catalog. Each product has a name, a short description, a product number, and a price in a structured order of appearance. However, this is not a database, it's just some printed pages. Even today, we all still work with huge amounts of data that was not digital born, from invoices to various reports. This is especially true for cultural heritage, where we often only have access to books and the like. It used to take months to analyze a pile of documents before we could start doing what we were supposed to do, which was to create new content. No more. AI is changing the way we work with semi-structured data. For example, this catalog of stone monuments from Roman period. It contains 11 categories of information, each delineated by a title. Traditionally, we would first build a database and then enter the information manually. With large data sets, such a process could take months. Now, however, we can use AI code interpreter and achieve this with a single prompt. We simply describe that we want to convert the text to a spreadsheet, provide an example, and AI code interpreter returns a downloadable file. The resulting table holds all the information from the text in a structured format. And as we saw earlier, this type of information can be analyzed with AI. In addition, it's relatively easy to transform the spreadsheet data into a web application that allows us to query the data and to publicly disseminate it. In this example, AI helped us to get from a catalog written as a Word document to a structured database quickly and efficiently. We can now query the data in the web application or use AI code interpreter for further analysis. However, in cultural heritage, we often work with old data. So let's look at an example where we start with an old printed book and we want to build a geodatabase. The example are medieval stone monuments called stečki. If we start with an old book, there are several levels of errors that are generated. First, the conversion of images to text. Second, older texts tend to be less structured. Third, the geographical location is not given as geo-coordinates, but as a textual description. We process the data in 4 steps. OCR, that optical character recognition, text to spreadsheet, data enrichment, and geoparsing. For the OCR, we used multimodal LLM because it was able to distinguish between line breaks and paragraph breaks. With the help of paragraph breaks, we were able to convert the text into a table, so similar as in previous example. However, both steps required extensive manual quality control and were far more complex than the previous example. So when we had Word, 1 prompt was enough. Here it was, let's say, 10 prompts or something like that. I will now focus on data enrichment. Data enrichment is a process in which we create new categories of data that we extract from the original text. For example, LLM was able to understand the description of the quality of monuments and categorize them as good, medium, or poor. Second example, LLM was able to extract the count of monuments for each location from the text. Well, sort of. For both tasks, it was only around 60 to 70% accurate, and to be honest, that was a bit of a disappointment. The most difficult step was geoparsing, a process that involves recognizing place names in text data and assign specific geographic coordinates to them. As you can see, this task is far more complex than any of the previous ones. We have a textual description and we need specific geo-coordinates. First, we match the place names from our text with data from OpenStreetMaps. The LLM got about 60% correct, about 20% false positives, and 20% false negatives. This result was in line with the expectations. You can see here one of the reasons for false positives, which is duplicate values. There are a particularly large number of missing place names in this area, as many villages were destroyed during the war in the 1990s. Traditionally, we would go in search of old maps, which is a tedious task. Instead, we used LLM to extract the information from the text, for example, 4 kilometers west of Trebinje. For the calculations, we asked the AI to use a tool called Wolfram language, which it duly did. With this information, we were able to build a web application just as previously with relative ease. Next stop, online geodatabase, better known as a web map. There is no ease when it comes to GIS, but AI makes life easier. First, we exported the data into the correct format using LLM. The data could be directly imported into our low-code GIS platform to create a hosted feature layer. Next, we built a web map, and finally, the application, which we deployed on the web. And here it is, a fully functional web map with all the bells and whistles, featuring our geodatabase created from an old book and now accessible to anyone with a link. Wait a moment, are there supposed to be so many stage key in the sea? It turned out that our geoparsing method was only about 60% correct. Once on the map, however, most errors can be easily recognized and corrected. You will notice that the color and size of the individual circles are based on fields that have been created with data enrichment. The color represents the quality, and the size represents the number of monuments. This geodatabase can now be analyzed, either with conventional GIS tools or with an AI code interpreter. We can immediately identify clusters of monuments that were not transparent when reading the book. They are here and here. This information can be used immediately, for example, to plan the next field campaign. When starting from non-digital born data, we should still expect considerable manual work. However, we estimate that we have saved around 60% of effort compared to only using the tools that were available 1 year ago. That was semi-structured data. We demonstrated how AI can help us transform a printed catalog into structured data that can either be analyzed with an AI code interpreter or used to build web applications that allow us to query the data and also to disseminate our findings online. Even in the most complex example, AI helped us to cut the effort by more than half compared to using the tools available 1 year ago. The last type of data we will look at is unstructured data. Unstructured data is text that was created for humans to understand and not for computers. The most common example is a folder of PDF files, like this reading list I keep on my desktop. But I never quite managed to stay on top of my reading. Imagine having a sneak preview of those articles at your fingertips. Or at your workplace, imagine you could literally chat with an archive of old reports, which you must consult to plan future activities. And thanks to AI, now you can. One of the most exciting recent developments in generative AI is retrieval augmented generation, or RAG. RAG combines the power of AI with your private data to create highly accurate and relevant content. As this image shows, it's a relatively simple concept. You create a prompt, RAG system searches your data based on that prompt, retrieves relevant content, and it sends the enriched prompt to the LLM, which generates the response. The great thing about RAG is that it's very cost-effective, and when implemented properly, the results can be excellent. However, as this image shows, building a production-ready system is actually very complex. We will not go into the details of advanced systems, but we will focus on what is available to each of us now. Let us take a look at RAG in action. We have developed an AI chatbot for archaeological LiDAR called Open LiDAR Toolbox Tutor, or OLIT for short. It was developed to chat about archaeology-specific processing of airborne LiDAR data. I realize that not everyone is a specialist on airborne LiDAR, so essentially it's a technique of airborne laser scanning, where you scan the landscape, and with some clever processing, you can filter it so that you create a digital terrain model only of ground, and this is where us archaeologists are able to recognize a lot of different features, archaeological features and sites and so on. And Giga will talk more about it. So let's send a prompt with a question on archaeological LiDAR, first to ChatGPT and then to OLIT. We are asking a very specific question about the terminology. As expected, ChatGPT provides a long answer that sounds correct. But is it correct? So let's just focus on one detail, the definition of DFM. ChatGPT's answer is on the left and the quote from the scientific text is on the right. ChatGPT correctly surmised that DFM is not a common term. Translation: ChatGPT doesn't have factual information on the subject and it will make its best guess. Everything after that point is not factually correct. DFM is in fact an archaeology-specific term, and ChatGPT doesn't know that. Here is the response from LOZIČ. It provides the correct answer. Digital feature model, or DFM, is an archaeology-specific model that combines the DTM with off-terrain archaeological features and so on. We can confirm that the answer is 100% correct and indeed more clearly written than in the scientific paper. But that's not all. It provides citations, it encourages the user to fact-check, and it contains direct links to the scientific papers in question. This is obviously convenient for the user, but it's also so much more. RAG is grounded in our own data, which makes it trustworthy. It provides direct citations, which makes it transparent. And it provides direct links to source data, which makes it explainable. So LOZIČ is as close to trustworthy, transparent, and explainable AI as the current technology allows. That was LOZIČ, our publicly deployed trustworthy RAG for archaeological LiDAR. Let's take a look at another example, a local and private RAG. There are several reasons to run RAG locally on your own computer or on your local network. It may be that the data needs to be private, or you will also want to run it locally if you have very large data sets, because this way it is cheaper or even free. We have set up a local RAG for our library with 500 scientific papers in PDF format. We have set it up locally because of the large amount of data and because we only have copyrights for private use, as we all do. We don't, when you download the papers, we do not have the copyright to distribute it publicly. To make it completely private, we ran the LLM locally, which requires an upmarket hardware, so think 5,000 euros or more. But as a result, we can literally chat with our entire library. The fact that the dataset in this RAG is so much larger than the one in LOZIČ makes it less precise. This RAG will not write the next scientific article for us, but it will be a great assistant. You can think of it as a private search on steroids. Here, we ask it to compare filters for archaeology-specific ground point extraction. The result is very detailed, it is factually correct, and most importantly, direct links to source documents are provided. This was RAG, an AI tool that enables you to chat with any type of data. We have shown how it works with unstructured text, but it can also be used with semi-structured or structured data. It's trustworthy, transparent, and explainable. Trustworthy, transparent, and explainable AI is one of the highest goals for the entire AI community and one of the reasons why the AI on-demand platform was created. Therefore, we believe RAG has great potential as we drive forward the process of digital transformation in the cultural heritage sector. If you're interested in building your own RAG, we have developed Be My RAG, a tool that will get you started. Just answer the 6 questions and you will receive information on tools and tutorials tailored to your specific needs. You can access this tool on the AI on-demand platform by searching for cultural heritage assets or on our project website. There you can also find out more about how we developed Arcus AI and LOZIČ chatbots if you're interested in building AI chatbots of your own. In conclusion, we have shown in this presentation how AI makes data conversations easy for everyone. We now have the power of deep analysis of structured data, giving us new and unexpected insights that were not possible before. We can use AI to efficiently analyze even semi-structured data. We have shown how an old book can be turned into a geodatabase that can then be further analyzed. But perhaps the most exciting opportunity is offered by RAGs. With RAG, we can query dozens, hundreds, or even thousands of documents with an ease that was previously unimaginable. I do not think I'm exaggerating when I compare the advent of AI in cultural heritage with the advent of computers some 40 years ago. However, there's one big difference. AI is coming at us at least 10 times faster. It may have taken a decade for every museum to gain an access to a computer, but every new LLM is instantly available to everyone. We are at the dawn of an exciting new era where we no longer need specialists to work with our data because AI will make data work for us. Before I hand over to the other speakers, I would like to leave you with some thoughts for policymakers and managers. The age of big investment in hardware and software is over. The time of upskilling and enabling your teams has come. What do I mean with this? Of course, the databases will remain an integral part of our workflows. But how and when we build them and how we use them is changing dramatically. The landscape of AI is evolving so fast that it's impossible to plan your investments even 1 year, let alone the usual 3 years ahead. As this table shows, none of what I have demonstrated today was available to non-developers 1 year ago. On the other hand, almost every tool is quickly available to consumers. The best thing you as a policymaker or manager can do is to upskill your teams to be able to integrate AI into their workflows. Enable them to find and use the tools and solutions that they need when they need them. Do this, and you and your team will prevail. Fail to adapt, and you will fall behind the curve in a New York minute. That concludes my presentation, and I'm giving the floor back to Edisa.